Alright, so this is going to be our last segment in the solution chemistry unit, and this is a concept that is more on the fundamental side. And what I mean by that is this is something that will absolutely follow you throughout the rest of your chemistry career. So when we store chemicals, usually we store them in their solution phase because frankly it's a little bit safer. And we want to know when we store those chemicals away, what is the concentration of the solution? Or in other words, how strong is that solution? So there's a huge difference between, for instance, a weak solution of HCl and a strong solution of HCl. If I pour, or spill is what I should say, a weak solution of HCl on my hand, it's not going to feel great, but I'm going to be okay. I need to get it cleaned up, but I can take care of it and it'll be fine. If it's a stronger concentration of the solution, then that's when I need to worry a bit more and be quicker in my actions, etc. So a way that we measure or mathematically describe how concentrated a solution is by using something called molarity. So molarity is a very simple equation. Okay, it's big capital M is the symbol for molarity, and the way that we calculate how strong a solution is, remember a solution is a solute dissolved in a solvent, is the moles or the quantity of the dissolved solute in the solution divided by the volume or the liters of the total solution. Now notice that this word is solution and not just solvent. Okay, that is important when you're making these calculations. Remember, the solution is the solute and the solvent together. So my favorite example when talking about molarity is using chocolate milk. Okay, and I know you want to get into an argument about whether you use powder or the syrup to make your chocolate milk. Frankly, neither of them compare to the carton that you get at the store. Not the jug, like the milk carton. It doesn't matter. It's delicious. Moving on. Whether you use powder or syrup, this concept works. If you just add a little bit, okay, your chocolate milk tastes disgusting. It's basically just like slightly flavored milk. But that would be a low concentration, right? Because that would be a small amount of your solute dissolved in your solution. The more chocolate you add, usually the more delicious, okay, until you hit that saturation point. The more moles dissolved, again, higher concentration, higher molarity. And remember, the volume would be the solute and the solvent together. And you're right, when you add the chocolate powder, the volume doesn't change that much, but it does, and we reflect that in the calculation. Okay, so symbols that you're going to see, big capital M, again for molarity. You might just see it written as moles per liter also, and that's totally fine. You might also see it written as just a number, which would be the concentration, in hard brackets like that. That's another way that this is represented. So if I had like a 2 molar solution of HCl, you might see it written like this, 2 molar HCl. You might see it written as 2 moles per liter HCl, and you might just see 2 HCl in hard brackets like that. Okay. All three of those work. We're probably going to stick with these two, but this you'll see come up in AP Chem. So obviously the higher the molarity, the more concentrated the solution. Okay. Very important that you always have correct units when you're making these calculations, and we're going to use dimensional analysis to accomplish this. So if you start with grams, for instance, of your solute, you need to convert that to moles. Anything other than liters for your solution volume, convert it to liters, but you guys know how to do that. So we're just going to do a few examples. Should be pretty easy peasy. The first one, we want to find the molarity, right? There's going to be 3 different variables, so this time we're looking for molarity of a 2,500 milliliter solution that has 6.3 moles of HCl fully dissolved. So in order to find molarity, I need to have moles of solute over liters of solvent. Okay, so that's just the way I'm going to set this up. I'm going to make sure that moles are on the top, liters are on the bottom. So if I have 6.3 moles of HCl, I'll just start with that. Okay, and I've got moles on the top, and I want to make it so that my volume of my solution, notice that this says solution, not just water. It's not that I take 2,500 milliliters of water and add it to the HCl, but I'm going to put this on the bottom. So 2,500 milliliters, and that's just going to be under 1. Okay, so no units are canceling so far, but that's fine. I've got moles over milliliters, which is a form of concentration, but I need to change this into liters. So I'm just going to do some metric dimensional analysis. I know that for every 1,000 milliliters, that's going to be 1 liter solution. Okay, my milliliters cancel, and now I have moles divided by liters, which are my units of molarity. Okay, throw this baby in my calculator, and I'm going to get 2.52, it's probably 2 sig figs, isn't it? Yeah, it is, whatever. 2.5 then moles of HCl over liters. Okay, I can leave it like that, or I can write it as 2.5 molar HCl. Okay, so if I have a solution sitting in my stockroom and it's labeled as 2.5 molar HCl, I know how strong that solution is, and I can dispense the volume that I want to use in whatever experiment I'm performing. So that's, again, how we're a really safe way, especially to store acids, okay, which is why we always have acids as aqueous. Next, we have a solution that has a total volume of 500 milliliters that has 300 grams of MgCl2, and we're going to assume those are fully dissolved. What is the final concentration? So again, I always want to make sure that my solute ends up on the top, my total volume of solution ends up on the bottom. So let's just do this. So we've got 300 grams of MgCl2. Okay, grams are going to be on the top just because that's my solutes, but I need to convert this to moles using the molar mass. It's really weird that I was not here to teach you guys this unit, but I assume you know how to do this. Okay, so I'm going to use the molar mass of MgCl2. So that means for every 1 mole of MgCl2, it's going to have a mass of 95.21 grams. Okay, so now I've got moles, which is great, and now I need to put that over my volume. So I have 500 milliliters. Okay, and then for every 1,000 milliliters, as you know, that's 1 liter. And I'm just going to make an executive decision to make this 3 sig figs because I don't want to do sig fig, or 1 sig fig, because that's how I feel. So we would do 300 divided by 95.21 divided by 500 times 1,000 would give us 6.30 molar MgCl2. So that's how strong that solution is. So if I were to compare these two solutions, this one right here, the MgCl2, would be stronger. Okay, in other words, it'd be a more concentrated solution. That does not tell me how chemically reactive the solution is. I'd have to look at the properties in my compounds here, but that just means per unit volume, there's more stuff dissolved in this solution down here than in this one. But as you probably have figured out already, you'd be more worried if you got this 2.5 molar HCl spilled on you than the magnesium chloride, because that's just a salt. I mean, don't do it, but you're going to be fine. Okay, so these two problems we solved both for molarity. Let's do a couple where we solve for something other than molarity. So in this case, we're saying how many grams. Okay, so my final unit should just be grams. I need to get rid of everything else. Of sodium hydroxide are needed, nice grams, nice, are needed to make 150 milliliters of a 4.0 molar solution. Okay, and here's your molar mass right here. So we want to end up with grams, and remember we want grams to be on the top. We're not solving for inverse grams. I'm going to start with my molarity because I know that's going to set me up correctly. And yeah, it says 4.0 molar, but I know that really means 4.0 moles of NaOH per liter of solution. Okay, so I'm going to start with it like that. I need to get rid of liters entirely. I don't have liters, I have milliliters. I can work with that. For every 1 liter, it's 1,000 milliliters. And I'm going to multiply by 150 milliliters over 1. Okay, liters are gone, milliliters are gone. My volume component is completely gone. Now I'm just left with quantity, which is great. I've got moles. I need to convert this into grams. I'm going to do that using the molar mass. So for every 1 mole of sodium hydroxide in my solution, that's equivalent to 39.99 grams of sodium hydroxide. Okay, so even though they're super far apart, moles of NaOH cancel with moles of NaOH. I am left with just grams, which is exactly what I'm looking for. I'm looking for the mass. Okay. That's fairly normal in terms of plugging into our calculator. No surprises there. So that would be, what, 24? Because we have two sig figs? Yeah, sure. 24 grams of sodium hydroxide. Okay, last one. This one's a little different because in this case we are solving for volume. Now in every other scenario we've had volume on the bottom as part of our ratio, and that's fine, but this time we want to end up with it on the top. Otherwise we'd solve for inverse volume, and that's not what we want. Okay, so what volume of solution would result from using 20 grams of CaNO3,2, so calcium nitrate, to make a 3.5 molar solution? So 3.5 molar, that means 3.5 moles of CaNO3,2 per liter. Okay, and you guys have seen me do this a million times. I'm going to flip this, okay, which I can do because it's a ratio and these two things are equivalent. Alright, so this is the same thing. It's just flipped. It's just a ratio. So for every 1 liter, this is 3.5 moles of calcium nitrate. And that's what I'm going to start with because that will allow me to have my volume component in my numerator, which is what I want. So I've got 1 liter over 3.5 moles of CaNO3,2. Okay. And now I'm off and running. And again, I'm solving for volume. So I need to get rid of moles. I can use my molar mass to do that. So for every 1 mole of CaNO3,2, the molar mass is 164.09 grams calcium nitrate. Okay. So moles are gone. I still need to get rid of grams. I don't want my mass component at all, and I can use the fact that I used 20 grams of calcium nitrate to make this solution. So I'm going to put that on into my numerator. Okay, and that would just be over 1. Grams cancel, and I am left with liters. Now be very careful when you're plugging this into your calculator. You can't just start with 3.5. You need to do 1 divided by 3.5 because this 3.5 is in the denominator. So 1 divided by 3.5 divided by 164.09 times 20. Okay, and that would give you 0.035 liters, and you could also write that as just 35 milliliters. Okay, so it's dimensional analysis all over again. Think about what units you want, think about what units you need to get rid of, and use the material and the information that you're given to make that happen. Been doing this in September. Lucky you. Alright.